Today we will discuss the principle of inclusion and exclusion. Now, the principle of inclusion and exclusion is a principle by using which we count the number of elements in the union of several sets. Suppose S is a set by the symbol modulus of S, we will mean the number of elements in that set. Now, what we are interested in is if we have several sets like A1, A2 and so on up to AN, where n is finite, and the size or cardinality of the set A I, which we denote by, let us say, modulus of A I, is less than infinity for all I belonging to the set 1 2 dot 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 n, what is the size or cardinality or simply the number of elements in the union A1 union A2 and so on union AN. Now, the principle of inclusion and exclusion lets us compute this precisely. To begin with, we start with n equal to 2. And instead of writing A1 and A2, we will consider the sets A and B. Now, we have this result number of elements in A union B is equal to number of elements in A plus the number of elements in B minus the number of elements in A intersection B. The question is, how do we prove this result? To check the proof, we will look at the Venn diagram consisting of these two sets. So, suppose this is my universal set U, and inside this universal set we have two sets A and B. Now, in general we do not have reasons to expect that A and B are disjoint. What we will prove are of course true when A and B are disjoint, but let us take the general situation where there may be intersections, finite intersection of A and B. Now, I denote the set A by this circle and set B by the other circle. Now, we see that there is a region which is inside A, but not in B, and this region is precisely A intersection complement of B. Then there is another region which is both in A and B. So, this region is A intersection B, and the other region somewhat symmetric is the region where which is in B, but not in A, and this is A complement B. So, A B intersection B complement is this region, A intersection B is the region shared by both A and B, and A complement intersection B is the region which is in B, but not in A. Now, it is not difficult to see that these regions are disjoint from each other. So, the number of elements in the region which is the union of these three regions is the sum of the number of elements in each of them. The reason is, as I have already said, that these regions are disjoint. On the other hand, we also note that if we take the union of these three regions, then we get the set A union B. Thus, we can say that the cardinality of A union B is equal to the cardinality of A intersection B complement plus the cardinality of A intersection B plus the cardinality of A complement intersection B. Now, we move further on. Now, suppose you give me the set A and tell me to split it up into two disjoint portions. I can of course split it up in this way: A intersection B complement union A intersection B. So, we have already seen that this is this portion and the portion A intersection B. Now, these two sets are disjoint, and we know that the union of two disjoint sets will have exactly the number of elements equal to the sum of the number of elements in individual sets. Therefore, we will have cardinality of A equal to cardinality of A intersection B complement plus the cardinality of A intersection B. But we see that the equation 1 contains an element cardinality of A intersection B complement, and equation 2 contains the same element. What we can think of doing is replace the cardinality of A intersection B complement in equation 1 by an expression that we derive from equation 2, but we will do that after the next step, because in the same way I can prove that cardinality of B equal to cardinality of A complement intersection B plus cardinality of A intersection B. Let us call it 3. Now, from 3 we see that A complement intersection B can be replaced over here in 1 by cardinality of B minus cardinality of A intersection B. If we do that, we have A union B equal to cardinality of A minus cardinality of A intersection B plus cardinality of A intersection B plus cardinality of B minus cardinality of A intersection B. Some cardinalities of A intersection B's are getting cancelled, and therefore, we will get cardinality of A intersection B equal to cardinality of A plus cardinality of B minus cardinality of A intersection B. Thus, we have got the result that we wrote down over here. We can solve some problems related to this counting principle. Let me write down one problem. Suppose 100 people in a class can speak French and 50 people can speak Russian while 20 can speak both the languages if each student in that class speaks either French or Russian, if each student in that class can speak either French or Russian, then how many students are there altogether? Now, let us denote by F the set of students who speak French, and by R set of students who speak Russian. Now, it is clear that the number of students who speak French is equal to 100, the number of students who speak Russian is equal to 50, and number of students who are in both the groups is equal to 20. And we have been told that any student in the class speaks either French or Russian. So, the total number of students in the class is the number of students in the set F union R, or the cardinality of the set F union R, which is given by cardinality of F plus cardinality of R minus cardinality of F intersection R, and therefore, we are going to get 100 plus 50 minus 20, which is 130. Now, let us look at another example, which I will leave as an exercise. From a group of 10 doctors, how many ways a committee of 5 can be formed so that at least one of Dr. A and Dr. B will be included. What I claim is that this problem also can be attempted by the principle of inclusion and exclusion. I leave it as an exercise. Next, we move to principle of inclusion and exclusion for 3 sets. Here we will take the 3 sets to be A, B and C. We will draw a Venn diagram showing the general situation. So, I have A here, A, then B and then C. Now, this region is A intersection B complement intersection C complement. This region is A intersection B intersection C complement. This region is A intersection C, or rather let me write A intersection B complement intersection C. This region is A complement intersection B complement intersection C. This region is A complement intersection B intersection C, and lastly this one is A complement intersection C complement. Let me write B first. So, I will write over here B, B and not the complement. So, let me remove this portion. So, this is A complement intersection B intersection C complement. Now, therefore, we can write down the cardinalities of ABC. Cardinality of A is equal to cardinality of A intersection B complement intersection C complement plus A intersection B intersection C complement plus A intersection B intersection C plus A intersection B complement intersection C. Incidentally, I have left out one set over here, this set, this is A intersection B intersection C. Cardinality of B in a similar way is A complement B intersection B intersection C complement plus A intersection B intersection C complement plus A intersection B intersection C plus A complement intersection B intersection C. Cardinality of C is A complement intersection B complement intersection C plus A intersection B complement intersection C plus A intersection B intersection C plus A complement intersection B intersection C. And if I sum all of them, then I am going to get we have this expression. Now, what we will see is that A intersection B complement intersection C complement, which is this portion, then A intersection B intersection C complement, which is this portion, A intersection B intersection C, which is this portion, then A intersection B complement intersection C, which is this portion, this is whole of A, and then we have A complement B C complement, this is this portion, and then we have A complement intersection B intersection C, which is this portion, and lastly we have A complement intersection B complement intersection C, which is this portion. All of them together gives me the cardinality of A union B union C. So, I can write cardinality of A union B union C, which is sum of these terms plus A intersection B intersection C complement plus A intersection B intersection C plus A intersection B complement intersection C plus A intersection B intersection C plus A complement intersection B intersection C is 5 elements. Now, if we consider these two terms, we will see that we get A intersection B, because this is A intersection B intersection C complement and A intersection B intersection C. So, together we get A intersection B. So, let me write down this is cardinality of A union B union C plus A intersection B plus this one and this one together gives me A intersection C, and lastly I have A complement intersection B intersection C. Therefore, I have an expression like this. So, A in union B union C is equal to cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of A intersection C minus cardinality of A complement intersection B intersection C complement. Now, if we consider the set B intersection C, then we see that B intersection C is A intersection B intersection C cardinality plus A complement intersection B intersection C. If I replace this above, I get A union B union C cardinality is equal to cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of A intersection C minus cardinality of B intersection C plus cardinality of A intersection B intersection C, which is the final result. Once we come to this point, we wonder that what should be the general form. We have seen for two sets A and B, what is the cardinality of A union B in terms of cardinalities of A, B and A intersection B. We have seen for three sets A, B, C just now an expression of cardinality of A union B union C in terms of cardinality of A, B, C and the mutual intersections. What about the general expression? In general, we can have a finite number of sets, each with finite cardinality, and we are interested in the cardinality of their union. Now, let me write the general statement. First, I write the header as the general statement of the principle of inclusion and exclusion. If AI I equal to 1 to n are finite subsets of a universal set U, then cardinality of A in union A2 union so on up to union A n is equal to summation I equal to 1 to n cardinality of A I minus sigma I comma j, where I is less than j, cardinality of A I intersection A j plus sigma I less than j less than k, cardinality of A I A j k, that is cardinality of A I intersection A j intersection A k, and it will go on like this to the final term 1 raised to the power n minus 1 A 1 intersection up to intersection A n. Now, this is the general form. Now, the question is that how do we prove it? Now, I will give a short argument of the proof. Let me write down proof. Suppose that an element x belongs to A 1 union A 2 union up to A n. Is in exactly M of the sets, say x belongs to A 1 up to x belongs to A m, and x does not belong to A m plus 1 up to x does not belong to A n. So, I start by considering an element which is in exactly m sets, and without loss of generality I assume that x is in the first m subsets and strictly not in the other ones. Now, the question is that how many times x will be counted. So, x if you look at this expression, then x will be counted m many ways. In the first sum, x will be counted in each of the terms A I equal to 1 up to m that is x will be counted m choose 1 times in I equal to 1 to n sigma a I. Similarly, x will be counted m choose 2 many times in sigma a I intersection a j. X will be counted m choose 3 many times in sigma a I intersection a j intersection a k and so on. So, if we keep on increasing the number of sets, then we will and count the number of times x will be counted, then we will find that we have a series. So, the x is counted in this way. So, x is counted m choose 1 many times in the first sum, and then in the second sum it is counted m choose 2 many times, but we subtract the second from the first. Then we add up the next one and we proceed in this way to go up to minus 1 raised to the power m minus 1 m choose m. Now, we see, so this is the total number of times any x belonging to a 1 union up to a n will be counted, provided that it is in m many subsets of the considered subsets. So, now we see the binomial expansion of 1 minus 1 raised to the power m, which is equal to sigma I equal to 0 to m choose I minus 1 raised to the power I 1 raised to the power m minus I, which is equal to m choose 0 minus m choose 1 plus m choose 2 minus 1 square plus m choose 3 minus 1 cube plus and so on up to minus 1 raised to the power m choose m. And remembering that m choose 0 is 1 and transposing, we will have 1 equal to m choose 1 minus, or just write plus minus 1 raised to the power 1 m choose 2 plus and so on plus minus 1 raised to the power m minus 1 m choose m. And so, we see that this sum appears over here and which is equal to 1. This means that when I consider the expression, let us recall that expression again. in this expression, if I take any x belonging to A1 union A n and see that number of times it is counted here and appropriately add and subtract those numbers depending on the signs, that adds up always to 1. So, any x here is counted once when I consider this total number of counts. Therefore, this total count is exactly this, and this is the general principle of inclusion and exclusion. I will stop here today, and in the next lecture we will work out certain problems on the principle of inclusion and exclusion in the general form. Thank you.